This video is on net ionic equations, what they are and how to write them. So before we do anything, any explanation of this idea called net ionics, we're just going to write this regular equation just like normal. Predict the products, consult solubility rules, and balance the reaction. Okay, because when we're doing anything in chemistry, we have to have a balanced reaction before we can go on and have any further discussion. Okay, so this is obviously a double replacement reaction. So my lead and potassium are going to switch places. So that puts potassium with nitrate. K is +1, nitrate's -1, so KNO3. And then it puts lead and I together. Now I is -1. Pb is a transition metal, but we can figure out the fact that because there's two nitrates, each with a -1, that Pb must be a +2. So I've got a Pb +2 with an I -1, so I2. All right, so from here, we need to balance and then do states of matter. So balancing, let's see, I have two I's on the right, I need two I's on the left, so a 2 here, and then that gives me two potassiums, also gives me two nitrates, so there you go. Okay, so what do I know about solubility? Well, I know that KNO3 has both a nitrate and a group 1 metal, so this is obviously aqueous, and I don't know about this one. I would need to consult my solubility rules. I don't have that chart on my video right now, but if you consult it, you're going to find that PbI2 is insoluble. And so this, of course, is the precipitate. In a prior video, we learned that some precipitates are white, some precipitates are colored, right? So I would ask you, is it possible that this precipitate has a color? And you should answer yes, because lead's a transition metal. Okay, now we don't know that for sure, because remember, not all transition metals produce color, but it's possible because lead's a transition metal. Okay, so this is what we call, a balanced chemical equation. It's also what we call a molecular equation. And I hate to tell you that this isn't really what this reaction looks like on an atomic level, because there's something that we have to consider. And the thing we have to consider is that ionic soluble compounds ionize in water. Okay, so to ionize means to break apart into their ions. So this is almost the reverse of writing a chemical formula. But what we are now discussing is the fact that any ionic soluble compound is going to ionize or break apart in the water. Now, that's kind of a broad definition, and I will tell you right now that there's an exception to that. However, this is not the time to learn that exception. That's going to come later. So for now, we're going to say that if it's ionic and soluble, it's going to ionize. So this is ionic and soluble, so is this, and so is this. So that means that those three compounds really don't look like that in water. So I'm going to give you a very simple example, which would be if I had NaCl in the aqueous state. Okay, so you might be inclined to think that if I put NaCl into a beaker of water, it would just kind of float around like this and life would be good. But that's not the case at all. NaCl is aqueous and it's ionic. It's going to ionize. So it's basically going to break apart into its ions, which would be Na+1 and Cl-1. And both of those ions are aqueous. So see, my beaker of salt water does not look like this. What it really looks like is this. Oops, I'm running out of room. Okay, because there are ions floating around. So unfortunately, even though this is the equation we work with all the time, it does a pretty poor job of showing us what's really happening during a reaction. And so we have to take this ionic soluble character into consideration when we're talking about these reactions. So this gets a little bit cumbersome, but what we're going to do is take this and ionize any species that should be ionized, okay? So we'll start with this one. We already said, yes, it's aqueous, it's going to ionize. So it's going to break apart into the lead ion, right, which we already said was +2, and into the nitrate ion, which is -1. Both of these are aqueous. I have to take into account, though, that I have 2 groups of nitrate. And so that 2 I'm going to bring out in front to say I have 2 of those nitrates. So this is going to take a while to get used to, but this is how we take into consideration the ionization of these compounds. So then we're just going to keep going. We know that potassium iodide is also going to ionize. It's going to ionize into K +1 and I -1. But I have 2 of the whole compound. So if I have 2 KIs that break apart, I'm going to get 2 K pluses and 2 I minuses. Okay. We said KNO3 is also going to ionize because it's aqueous, so it's going to ionize into the potassium ion and the nitrate ion. Polyatomics never break apart. Both of these are aqueous. And again, I have a 2 out in front, so it's going to give me 2 potassiums and 2 nitrates. And then I come to the final one, which is the PBI2, but it's a solid, okay? It's insoluble. It's not going to ionize, so we're just going to write it as is, okay? This is called, I think it's called a complete ionic equation, and it's called a complete ionic equation because it shows you the ionic behavior of these things that do in fact ionize. Okay, so actually this is a much more valid representation than this because it's taking into account that these things ionize. But from here we have one other thing we need to address, and that is that in chemistry we encounter something called spectator ions. Okay, now you're familiar with the word spectator because if you go to a football game or a basketball game and you're a spectator, you're sitting in the stands and you're watching, right? You're not part of the game per se. You're just watching the game. In chemistry, we have the same idea where we have ions who are kind of just watching. They're not really involved in the chemistry of what's happening. And the way you spot a spectator ion is that they are exactly the same as a reactant and a product. So I'm going to define that first. So spectator ions do not participate in the true chemistry. They are exactly the same as a reactant and a product. So if we go back to the equation I just wrote, we're looking for an ion who appears on both sides of the equation who's exactly the same, hasn't changed a bit, okay? And there are 2 of them. The first one is the 2 NO3 minuses, because look, 2 NO3 minus aqueous, 2 NO3 minus aqueous, they are spectators. And so what we're going to do is eliminate them from the equation. Because did they change? Nope. Did they go through any chemical reaction? Nope. They're just hanging out in the beaker. The other spectator is the potassium ion. 2 K pluses and 2 K pluses, nope, remained unchanged, right? Nothing happened to them. So once we remove the spectators, what's left over is the true chemistry, and that is called the net ionic. And so what we do is write down who's left. So we have a Pb +2 ion. We have 2 I minuses, or -1s, and we created the precipitate of PbI2. This is the net ionic equation. A net ionic shows the true chemistry and eliminates spectators. Okay. okay? So you might say that's an awful lot of work to get a little net ionic, okay? It is. There are a couple shortcuts that we can talk about, but it's important to understand how we got from this equation to this equation, okay? And there are times when you will be asked to write a net ionic, and there's a reason for that. So it's important that we know how to do this. Okay, so let's do some practice. At any time, in a practice session, you're welcome to pause the video and try it on your own, because that's pretty important to do. Okay, but I'm just going to go right into this. So, all right, solutions of calcium chloride and sodium carbonate are mixed. All right, calcium chloride, that's a +2 and -1, so CaCl2. It's aqueous because it told me it was a solution. And sodium carbonate, it's a Na+1, CO3 -2, so Na2, CO3, also aqueous. Double replacement, they're going to switch partners, leaving me with CaCO3, it's a +2, -2, and Na+ and Cl-, so NaCl. I know without a doubt that NaCl is going to be aqueous. I don't know about calcium carbonate. So if we consult the chart, we actually find that it is insoluble. This is a precipitation reaction, definitely going to see something happen, and so we are going to have a net ionic. So, let's go through our process. So in this case, I'm going to break apart anything that's aqueous. So this one, and this one. And then I'll cancel my spectators. So I have Ca +2 and Cl -1, but I have 2 Cl's. Both are aqueous. I have Na +1, CO3 -2, but I have 2 sodiums. Both are aqueous. I'm not going to ionize calcium carbonate. It's the precipitate, but I am going to ionize the sodium chloride. And so from here, we eliminate the spectators. I forgot to balance my equation. Whoops, guys, oh my goodness. So I had 2 of these up here, sorry. So then that gives me 2 of these and 2 of these. And see, I caught that very quickly because sodium's a spectator, but I had 2 sodiums over here, and before I balanced, I only had 1, which means I couldn't have canceled them. That means I hadn't balanced my equation. So that was my fault, and I apologize. Sodium plus is a spectator, so is chlorine. So my net ionic is going to be the calcium ion combining with the carbonate ion to form calcium carbonate. This is my net. Now, you might be on to me with these 2 as an example, and here's the shortcut, okay, but this only works in certain circumstances. If the reaction is a double replacement, okay, if the reaction is a double replacement and the situation is an aqueous and an aqueous make a solid and an aqueous, okay, or an aqueous and a solid, whatever. If that's the case, the net ionic will always be the ions that form the precipitate every single time. I'll say that again. If it's a double replacement reaction where you have everything aqueous except for your precipitate, the net ionic will be the ions that form the precipitate every single time. However, in just a minute, we're going to encounter a situation that's not like that. But we'll do that in a second. So, B, solutions of silver nitrate and potassium phosphate are mixed. Okay, silver nitrate, +1, -1, aqueous, plus potassium phosphate, K +1, phosphate -3, K3, PO4, aqueous. Double replacement, switch my products. Potassium and nitrate, +1, -1. And silver and phosphate. Silver is +1, phosphate is -3. I know this is going to be aqueous. It's a group 1 and a nitrate. See how quickly I'm moving? Because this is stuff we should know. Silver phosphate, I don't know, I got to look it up. Find out that it is in fact a solid. This is a precipitation reaction, and it fits what I just told you. Aqueous, 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 precipitate. If that's the case, we can cheat. We can cheat by saying the net ionic is going to be the ions that make the precipitate. So I would need 3 silver +1s and 1 PO4 -3. Now, if you don't believe me, you can go through the full I did it again and I forgot to balance my reaction. You guys. Okay, there. Anyway, however, the net ionic is going to be the same. Okay, like I said, if you don't believe me, you can work it out all the way through, but I promise you that's the net. But sometimes we encounter a situation like this, and this one's different. Okay, so C says a piece of magnesium metal is dropped into a solution of hydrochloric acid. Okay, so magnesium metal, that's a solid. Hydrochloric acid, H and Cl, +1 -1. A solution, it's aqueous. This is not a double replacement reaction. This is a single replacement. I have to consult the activity series, but when I do, I find that magnesium is more reactive than hydrogen, and so magnesium is going to come in and kick out hydrogen. This is going to be an interesting reaction because when hydrogen gets kicked out, it's a diatomic. It's H2, and its state of matter is a gas. And when Mg and Cl get together, it is Mg + 2, Cl - 1, so MgCl2. Now, this is when we have to start considering the fact that I had an aqueous substance to begin with. There's water in this reaction. So we now have to ask ourselves, will this thing dissolve in water? If you check your solubility rules, the answer is yes. So this is aqueous. Okay, so what now? This one's not a double replacement. We can't cheat. Okay, it's harder than that. So I have to balance first. Goodness. Okay, so when I balance, I have, I need 2 H's. So 2 H's takes care of my Cl's. That was easy. When I do a net ionic, I ionize anything that's aqueous. So I'm only going to ionize this, and I'm only going to ionize this. So H plus and Cl minus, both aqueous. I have 2 H's and 2 Cl's. Hydrogen gas does not ionize, but magnesium chloride does. I have 2 of them. And now I look for my spectators and be very careful because there is only one spectator and it's the 2 chlorine minuses. A lot of times I'll have students tell me, well, magnesium's a spectator. No, it's not. Magnesium went from a solid with no charge to aqueous with a +2 charge. It changed. Okay, it's not a spectator. So this net ionic looks different than any net ionic we've done before. So single replacement reactions and their net ionics are a little bit tricky. Okay, and so we'll be doing more practice with these later. But remember, a net ionic shows you the true chemistry by eliminating the spectator ions. So to write a net ionic, you write your reaction, you balance your reaction. Don't forget, like me, you break apart, I shouldn't say break apart, you ionize anything that's aqueous, and you cancel the spectators. And that's how you come up with a net ionic equation.